So the next speaker is Professor Phillip Griffiths. This is the first part of his special lecture, and he is going to talk on the projectivity in Hodge theory and algebraic.
Thank you, and thank you for fitting me into the conference, even though the topic is not directly related to this conference. I think this talk will be largely informal and somewhat historical. I think I want to get a glass of water. I left one back there. Now, let me. Yeah. Great, thank you. The use of curvature in algebraic geometry is not so common nowadays. There's a very active group who work on refining vanishing theorems using curvature arguments with singular metrics, things like that. There's also the whole activity centering around K-stability and special metrics. But generally speaking, I think looking back, a lot of interesting things started with curvature arguments that either proved something or suggested something, and then they go into the domain of algebraic geometry. Algebraic proofs are given usually, and the role of curvature, which is not algebraic, recedes into sort of the historical background. One of the beginnings of the relation between curvature and Hodge theory is, of course, the Kadara vanishing theorem. There you have a Kähler metric, so that's Hodge theoretic, and you have a positive line bundle, which for Kadara meant that it had a metric whose Chern form was a positive definite 1-1 form. And then you've got a vanishing theorem for the vanishing of cohomology, and that under those assumptions. That, of course, sort of opened the floodgates to vanishing theorems, where you have various refinements, the cohomology refinements, and very delicate vanishing theorems, again using L2 Tibor methods, where you have multiplier ideals coming in and so on like that. What I'm going to be talking about is a slightly different set of, well, really historical developments. Let's see if I can get this to work. Yes. So I'll make some introductory comments and then just review basically the notation from Hodge theory. Yesterday you heard in Rodolfo's talk an introduction really to Hodge structures and variation of Hodge structures, and I'll just go back over that briefly. And then I want to talk about the use of curvature arguments in I'm trying to get this thing to work. Yeah, use of curvature arguments in general type questions and hyperbolicity questions and what's called the Iotaka conjecture. So to give the algebraic geometric background, if you start with a smooth algebraic variety, then quasi-projective need not be complete. Then there are topics really of general continuing active research, interesting properties that the variety might have. One is that it is of log general type. So that means that there's a smooth completion to a compact, smooth algebraic variety where you've added a reduced normal crossing divisor, points at infinity. And the log general type means that if you look at the differentials of top degree and you allow logarithmic differentials, so if z equals 0 is the equation of one of the hypersurfaces at infinity, you allow dz over z, otherwise it's holomorphic. So that's what log z means. You just add the logarithmic derivatives of the local defining equations of the normal crossing variety. And then the property is that the top degree differential, the canonical bundle with logarithmic poles, is big. So it's like general type, only it's logarithmic general type. If z is empty, then that's just the same as saying that the variety is of general type, because the canonical bundle has maximum Kadara dimension. Okay. It's independent of the smooth completion of the variety. So it's really a property just of y, and this statement is independent of the z that you add on. A second potential property that's of interest is that the one forms with logarithmic poles is big. So that's now a vector bundle. This is a line bundle. This is a vector bundle. And again, to say that it's big means that the symmetric powers have lots of sections. Or the way that it will be used today is whenever you have a vector bundle, you can take the corresponding projective bundle. So the fibers are the duals of the projective spaces of the original bundle. You have the standard line bundle called O of 1 on the total space of the projective bundle, and that should be big in the sense of line bundles. So these involve differential forms of top degree. These are one forms. A third condition that is, again, talked about, is discussed in many different ways now, is that the back this up.
It's going to.
Okay. So hyperbolicity, the definition we'll use is that a holomorphic mapping into the variety should be constant. Okay, so it's like a Picard theorem. You take projective line, take out 3 points. That's hyperbolic. That's the classical Picard theorem. There are several notions of hyperbolicity. That's the Picard one. The big Picard one is that any mapping of an algebraic variety to Y is algebraic, no transcendental mapping. So that's the one we're going to be mainly concerned with. There's also the notion of hyperbolicity modulo a proper subvariety. And that's given by there being a proper algebraic subvariety such that any holomorphic mapping has its image in this proper subvariety. So if you had something that was hyperbolic and you blew up some lower higher codimension subvariety, then it would be hyperbolic modulo that because you've got P1s in the fiber of the blow-up. So there are relations among these three properties. Suitably interpreted, the one on holomorphic one forms intends to imply the one on top degree differentials as well as the hyperbolicity. So that's in a way the strongest of the three properties. So the purposes of, see if I can, yeah. No. So the purposes of the talk today and the one tomorrow will be to discuss these properties when Y parameterizes a family of Hodge structures. Okay. So very special circumstances arise when you have that situation. In the geometric case, and this is what to have really in the back of your mind, if you would have a family of smooth projective varieties, and you look at the Hodge structure on the fibers arising from the cohomology of the fibers, then the Y that we'll be interested in is the one that we'll be discussing these three properties concerning. We'll first discuss these properties from a Hodge theoretic perspective when Y parameterizes a variation of Hodge structure that Rodolfo talked about yesterday. In the geometric case, additional things happen of interest, and I'll talk about those. And then the case where the XY are only assumed to be of general type. In the classification of algebraic varieties, the Itaka scheme for classification, you reduce to studying fiber spaces where the fibers are of general type or of, if you like, Palladials. Okay. So there's extensive literature on all of these, and at the end of the slides, there's some selected references. A recent one is the paper by Zoe, and it sort of gives a detailed overview of the whole subject. So, yeah. So an informal survey of the results are this, that if the differential of the period mapping is generically injective, so that means as the Hodge structure is varying, it varies non-trivially to first order at a general point. So in that case, then all three of these properties hold. It's log general type, the holomorphic one forms are also of log general type, and it's hyperbolic. So what that's saying is that if you have a variety that parameterizes a family of Hodge structures in a generically non-trivial way, then you have these strong properties of the canonical bundle, the cotangent bundle, and hyperbolicity. In the geometric case, if you have local Torelli at a general point, that's the same. That implies then that the differential of period map is generically injective and all these properties hold. So you may say, well, how strong a condition is it that the period mapping be locally injective? Or another way of phrasing it is, when can you have a one parameter family of, say, algebraic varieties where the Hodge structure is locally constant, doesn't vary? There, the condition is that the the necessary and sufficient condition is that the monodromy group, which we'll talk about, should be finite. So it's a topological condition that is necessary and sufficient that the family of Hodge structures doesn't vary non-trivially. You see, we only have the big Picard theorem modulo a proper subvariety. So I think it's basically clear that one implies two in the previous slide. Whoops. Our pointer is, no. Let's go back to Rodolfo, sorry.
Here.
So I think it's basically clear that two implies one. If locus rarely holds, then you have, that's more or less by definition. And then you have all three of these properties. For C, you only will get Picard modulo a proper subvariety. That's the subject of well-known conjectures that have a lot of arithmetic significance. That if you have a variety of general type, or one in the complete case, or in the quasi-projective case, log general type, then there should be a proper subvariety such that by definition, the complement is hyperbolic. That is, any map of C into it, any entire holomorphic mapping ends up with the image in this proper subvariety. There are arithmetic analogs of this that I'll discuss later on, and sort of a relation between curvature on the one hand and arithmetic properties of algebraic varieties on the other. So that is basically clear that one implies two, and this is what I just said. For in the geometric case to have the result, what you need is that for general Y, the moduli of the fiber moves non-trivially on the base. Okay, this is usually saying that the variation of F is the dimension of Y, where F X to Y is the map in question. And that's the basic assumption, that the variation of F should be the dimension of Y, and that the fiber should be of general type or log general type. That's the log version. A further property in the geometric case is the Iotaka conjecture. That if you have a completion of this map where these are smooth, then the Kadara dimension is sub-additive. The Kadara dimension of the total space is bigger than or equal to the Kadara dimension of the fiber and that of the base. You notice here, we're just assuming the Kadara dimension of the fiber is equal to the dimension of the fiber. It should be of general type. Kadara dimension involves not just the canonical bundle, but powers of the canonical bundle. So the interesting point here is how to extract Hodge theoretic information from powers of the canonical bundle. If you have just the canonical bundle, that's holomorphic differential forms of top degree. Those always give cohomology classes. That's part of a Hodge structure. But if you have differential forms that are sections of a power of the canonical bundle, it's like dz raised to a power k, then there's an associated Hodge theory, and that's one of the interesting points in this Iotaka conjecture. And that's what I was just discussing. How can Hodge theory be used to derive families of algebraic varieties from the pluricanonical systems, not just the canonical bundles? So there's a vast literature on all of these topics. Although the formulation of these is purely algebraic geometric, the original proofs used Hodge theory, and in fact the curvature properties of the bundles that arise from Hodge theory provide heuristic arguments. So in the proofs of these results, the arguments generally and frequently encounter technical issues involving what happens when the varieties acquire singularities. And that gets into the complex analysis, the L2 D-bar methods, and so forth. So for the Hodge theoretic preliminaries, you start with a smooth projective variety, reduced normal crossing divisor, and you assume that you're given over Y a variation of Hodge structure weight n. So that implies, as Rodolfo said yesterday, you have the Gauss-Menin connection and the Hodge bundles. And importantly, you have the polarization given by the horizontal bilinear form on each fiber. So when you have a Hodge structure, there's the notion of polarized Hodge structure. That means that you have two bilinear relations on the Hodge, the HPQs. One is just an equality, giving some orthogonality between the different HPQs. The other, which is the important one for this, is that you have a positivity of the Hermitian inner products given by taking the HPQ tensor as conjugate. There's a Hermitian form and should be positive or negative depending on the parity of P if you're talking about HPQs. So the general philosophy is if you have a family of Hodge structures that are polarized, then you have the Hodge bundles. And the Hodge bundles have canonical metrics. Once you have a complex vector bundle with a metric, you have a canonical connection, the Chern connection. And that connection has curvature. And the fundamental observation is that for families of Hodge structure, those curvatures have very special properties. They have both sign properties and algebraic properties. So the data of a variation of Hodge structure is equivalent to a period mapping where you look at the period domain of all Hodge structures with given HPQs and a polarization, and you have a holomorphic mapping modulo the global monodromy group. So whenever you have a local system that is an integral connection, then you have a monodromy group because you can take a base point, and you take flat sections, horizontal sections for the flat connection, parallel translate around an element in the closed loop in the base, that generates the monodromy group. And you should locally be able to lift the period mapping to the space of Hodge structures. There'll be fixed points of the monodromy group. So if you want to work in, you can work in this situation. It requires more technical work, so it's just simpler to assume that the thing is locally liftable. So whenever you have then your local system, in particular if you have a variation of Hodge structure, you look at the divisor at infinity. So that's a normal crossing divisor. A loop around each of the branches gives a monodromy matrix. And one of the special properties of the monodromy is that they are quasi-unipotent. So the eigenvalues are roots of unity. So some power of the monodromy is unipotent, just has ones on the diagonal. So it's essentially the exponential of a nilpotent matrix. So that's the local monodromy theorem, which the original proof was a curvature argument that I'll give later on in the talks. There's also the global monodromy theorem. You have a quasi-projective base and the variation of Hodge structure over that. That's global. Then for the monodromy is semi-simple. It's the opposite of unipotent. So monodromy is really king in Hodge theory. The monodromy is the most subtle invariant in the whole business. Locally, it's unipotent. Globally, it's semi-simple. So you have the space of Hodge structures. You look at the compact dual, that just means you put in the first Hodge bilinear relation. And there are canonical extensions of these Hodge bundles across the divisor at infinity. So just to explain that for a minute, the Gauss-Bonnet connection is a flat connection, so it's like a system of ordinary differential equations. And those have regular singular points. So what that means is that the connection matrix has only logarithmic poles in it. So Deligne's canonical extension, let's assume the eigenvalues are all 1, then you simply allow sections that have at most a first order a log pole along the divisor at infinity. So more specifically, the Gauss-Bonnet connection goes from the Hodge filtration to 1 forms with log poles, and you can take the residue of the Gauss-Bonnet connection as you go around, and that's the monodromy. If you have an intersection of components at infinity, then there's a monodromy cone, and I'll talk about later, you have in this, for the whole monodromy cone, as long as you go into a non-singular part of the divisor. So think of 2 curves, you go into the open part of each or to the point of intersection, then you get what's called a limiting mixed Hodge structure. So there's a well-defined Hodge theoretic object in the limits. Again, the proof of the existence of the limiting mixed Hodge structure due to Schmidt was based on curvature arguments. The curvature has a sign properties that lead to estimates, and he used those in a very fundamental paper to show the existence of limiting mixed Hodge structures. So again, curvatures lurking in the background here. That was one variable case that Schmidt did. There's several variable cases was by Katani, Kaplan, and Schmidt. Again, curvature is going to come in a way that I'll explain. You can say, well, suppose you have no monodromy around infinity. Okay. There are plenty of families of algebraic varieties where you have a singular variety over the disk, say, where you have smooth varieties except over the origin. You have a singularity. And there are plenty of examples where the local monodromy is finite. For example, a rational singular point on the surface. So it's a general fact that even though the variety may be singular, the Hodge structure fills in. And so the image, you can assume then, by filling it in, that the period mapping is proper. You just add the Hodge structures you get in the limit. They're pure Hodge structures where you have finite monodromy. And a recent theorem by Baker, Bruno Barbie, and Zimmerman shows that the image is an algebraic variety. So even though the integrals that arise in Hodge theory, they're integrals of algebraic differential forms over topological cycles, those are highly transcendental objects. But nonetheless, the image is an algebraic subvariety in this analytic variety, not algebraic. And moreover, there's an ample line bundle, which I've just written the fibers of what it is over the image. Okay. So this theorem, a theorem proven 2-3 years ago, is a long-standing problem using a new technique of O-minimal structures. And that led finally to a proof that you get not just an analytic variety. Once you know this is proper, this is an analytic variety. They proved it's algebraic, and here's an ample line bundle. So the first and second Hodge-Riemann bilinear relations, you give metrics in the Hodge bundles, and you have associated curvatures. And again, these curvatures have sign properties, they have algebraic properties, and they also have very interesting singularity properties. So to summarize these singularity properties of the metrics and curvatures and their Chern forms. So the elementary symmetric functions of the curvature matrix are differential forms. Those represent the Chern classes in the Ron cohomology. And those have been analyzed. Basically, to summarize what comes out is that as the Hodge structure degenerates, the algebraic varieties degenerate, the Hodge metrics become singular. Because of the regularity theorem, the fact that Gauss-Menin connection has only first order poles, the metrics of the Hodge bundles are logarithmic. So they're polynomials in powers of the log, positive and negative, or well, in powers of the log, but no, powers of the log, positive and negative. They're Laurent polynomials, if you like, in the logs. Okay. So that's the metric. You might say, well, what about the curvature? To get the curvature of a metric, you have a positive function. Say for a line bundle, you have a positive function like a Laurent polynomial in logs, and you take dd bar log of that. So you're taking dd bar log of something. Ordinarily, you're going to get, well, it's a mess, but you're going to get singularities that are not controllable. You can't really say much about them in general. What happens in the Hodge-Riemann case, though, is that the Chern forms, as differential forms, are not smooth, but they're close to smooth. They're in L1, so they're integrable. Okay. And any integrable differential form defines a current. You can integrate it against smooth things and give a finite number. So they define currents, and one knows that when you take the cohomology of the space of currents, that's the same as the cohomology for smooth forms. And these currents then define the Chern classes of the extended bundle. And of particular importance is not only that the Chern forms have, they are themselves closed positive currents in L1, you can integrate them, but you can also wedge them together. So it's not just individually the Chern forms have controlled singularities, but the whole exterior algebra does. So for example, if you take powers, just formally multiply, these are Chern forms. The coefficients are, well, this is, let's say, the first Chern form. It's just a one form, or one form. Multiplying is the same as taking cup product in cohomology. And they can also have the property they can be restricted to the strata. And there they represent the Chern, the first Chern class in this case, of the canonically extended line bundles. So the way to think about it is, even though the Hodge structures are degenerating, the singularities are so well controlled that you can operate with the Chern forms of the canonically extended Hodge line bundles, Hodge vector bundles, just as if they were smooth. Going back to the theorem I mentioned before by the BBT theorem about the image being a quasi-projective variety, there's a stronger conjecture that says that if you take this line bundle that was on the previous slide, just the tensor product of the determinants of the Hodge filtration bundle, you take that line bundle that extends to an ample line bundle on the closure here, and the conjecture is that it's semi-ample. So because of the properties of the Chern forms, one knows that it's represented by a differential form by a current that's non-negative of type 1,1 and positive except on lower dimensional things. It's a standard problem when you have something that's big, so it will be big. A standard problem that arises is to show that the thing is semi-ample. That is, that the base locus of powers of the base locus given by zeros of powers of a bundle is eventually empty. Or if you like, a high enough power, the global sections generate every fiber. So this is a conjecture. I think there's been quite a bit of work on it, but it's never been proved to show that this canonically extended line bundle is semi-ample. It's a well-defined statement because if you blow up things, semi-ampleness goes along with it. So it's a birational type of statement. So it's well-defined, and a very nice open question. And in fact, if you had that, then you could take its proj, that's a projective variety, and this would be then a sort of canonical completion of the space of Hodge structures for a family of smooth varieties. You want to know, take the family of all Hodge structures, is there a canonical minimal completion of that to a projective variety? In the classical case of abelian varieties and K3s, the answer is yes. You have what's called the Satake-Bailey-Burrell compactification. So that's a complex compactification of a quotient of d by gamma. And you have an extension theorem due to Burrell that the period map extends, and that gives you the closure then, well, the image of the extension gives you a minimal compactification of the space of Hodge structures associated to a family of smooth varieties. This conjecture would prove that in general, not just for abelian varieties. The reason I've singled out abelian varieties is that's the only case in K3s where the period domain is Hermitian symmetric. It's a classical type of bounded symmetric domain. And those have, by a lot of work over the years, Bailey-Burrell for the minimal completion, the toroidal completions for the maximal one, the desingularized one. Those have completions that are much studied, the d by gammas. In the non-classical case, once you get to algebraic surfaces and higher dimensional things, the d is no longer Hermitian symmetric. The quotient d by gamma has no non-constant meromorphic functions on it at all. It's a strange type of complex analytic thing. You have in it the subvarieties, though, which are images of period mappings that are, or should be, algebraic. Skip that. A second conjecture, which is related, is just this. Oops, let me go back up one. Yeah. So suppose that you know that this bundle is semi-ample. So the conjecture is that, so I'm going to state it a special case of it. Assume that the period mapping is locally 1-1 on the open part. So you're adding some stuff to a mapping that's basically an immersion. And the stuff you're adding are just the branches at infinity for the normal crossing divisor. So you can ask for your original parameter space, your y with a z added. The image is an algebraic variety that has a semi-ample line bundle on it. What's an ample line bundle on the original parameter space with a normal crossing divisor? And the conjecture is that a high enough power of L minus a linear combination of these is semi-ample. Okay. So the image is supposed to be projective and L is supposed to be ample on it. The domain that you started with, the pullback of L will be semi-ample, but to make it, to make the whole thing semi-ample, you have to subtract off some linear combination of the divisors. So this particular conjecture it has been done in the case where the parameter space is two-dimensional, and it's subtle because the linear combination of the branches in infinity that you take out, that you subtract off from this line bundle L to make it semi-ample, those have positive integer coefficients, but you cannot choose them all to be 1. The choice of those coefficients reflects the sort of nature of the singularity that you get in the image of the period mapping. So, for example, suppose you have a two-dimensional parameter space, you have a smooth algebraic surface and a normal crossing divisor, that's a bunch of curves, and those curves are contracted to give you the image of a period mapping. So it's a surface with a normal singularity. What about your ample line bundle? You cannot just subtract off, what is that? It's on silent, I don't know why it went off. You cannot just subtract off the sum of the exceptional curves that you've contracted with coefficient 1. You have to put in multiplicities that reflect the nature of the singularity, the normal singularity, to get something ample. So coming to general type, I'll say a few words about this and then I'll stop for today. So the proof that if the period mapping is generically injective, that the parameter space for the family of Hodge structures is of log general type. There are now a number of proofs of that. I think the first one, among the first ones, was by So, and it uses some interesting properties about the curvature of these Hodge bundles. Okay. So the exact statement of the theorem is that the differential amount of the period mapping is generically injective, then this is log general type. So following Simpson, one usually associates to a variation of Hodge structure a Higgs bundle, which is the sum of the FP mod FP plus 1s, and theta, which is the differential induced by the Gauss-Menin connection. The E's have Hermitian metrics, and you have this integrability condition. That's the delta squared equals 0, the flat connection. These are the Chern connections on the Higgs bundle, compatible with the metrics, the D double prime is D bar. That characterizes the Chern connection. It's like the Levi-Civita connection preserving the metric, but the 0-1 part of it is D bar. Curvatures are 1-1 forms with values in the endomorphism, matrix value 1-1 forms. And this is the formula for the curvature. It's the sum of the differential of the, or if you like, the map induced by Gauss-Menin going in two directions. One is increasing at P, the other is decreasing it using the adjoint. So what the curvature form then is a difference of positive terms. It's not positive or negative, it's a difference. You'll notice that if one or the other, theta of E is 0 or theta star of E is 0, that means that you're at one end of the Hodge decomposition, and theta runs you to the next piece over. If you're at the end, you just get 0. Same thing for the adjoint of theta at the beginning. Then you have a sign. So it's the difference of non-negative terms. And one of the basic observations is that even though it's a difference of terms, of positive terms, if you're in the kernel of theta, then you get a sign. Okay. So the way that this is applied in Hodge theory is based on that observation. Due to so. And there's a condition that if the curvature is less or equal to 0, if it's equal to 0, then you have an invariant. It's not only d bar invariant, d bar is 0, but it's invariant under the 1, 0 part. It's a flat subbundle. So what that's saying is that at the ends of the Hodge decomposition, if you don't have a positive definite curvature form or negative definite, then actually that little piece on the end is locally constant, killed by Gauss-Bonnet. So what that's going to tell you is eventually, well, I'll just say it in words. Suppose, just picture the Hodge decomposition, and suppose that the a better way to do the argument, so you can see it on the overheads. Another consequence that involves the curvature of these Hodge bundles is concerning the tangent bundle. So you have the Hodge bundles; those have Hodge metrics in them. They have curvature. The curvature form was in the previous overhead. You also have induced metric in the tangent bundle if the period mapping is locally 1, 1. If it's only generically 1, 1, you get some singularities, but those, as I've said, can be managed. So the next property that the sign property that the curvatures has is that the biholomorphic sectional curvatures are non-positive. The holomorphic sectional curvatures are negative bounded from above. So it's somehow a negatively curved object, this parameter space. And so the bisectional curvature is less or equal to 0, and on a Zariski open set in pairs of tangent vectors, it's strictly negative. So the holomorphic sectional curvatures have to do with the canonical bundle. The holomorphic bisectional curvatures have to do with the cotangent bundle. So these two statements are going to translate into information about bigness of the canonical bundle or the log canonical bundle and of the log omega 1 bundle, 1 forms. So this is just going over what you have to do to prove the theorem. What I'm going to do, I'm not going to go through that argument. I guess I'll skip that. Yeah. So this is another conjecture involving the curvatures arising from a family of Hodge structures. So whenever you have this family of Hodge structures, you have the Chern form of the line bundle L that I mentioned. That's a positive, definite 1-1 form outside of places where the differential of the period mapping fails to be injective. So its top exterior power gives you a volume form. So there's a canonical, from the family of Hodge structures, you can think of it as saying that there's a canonical volume form on the parameter space. Given any volume form on a complex manifold, you have, it looks locally like this. And this is what it would look like in infinity if you're in the log case. And the Ricci form is just dd bar log of that. It's a closed 1-1 form that represents the Chern class in cohomology. So we can take the volume form arising from the family of Hodge structures and the curvature, the calorimetric on the part where the differential is injected, you get the usual Ricci form. And that gives you the positivity of the canonical bundle. So it's not only is the canonical bundle big, but at the places it has a differential form representing its cohomology class that's positive semi-definite everywhere and positive definite on the Zariski open set. That's enough to make any line bundle big that has a metric whose curvature has that property. So the curvature of the tangent bundle to the parameter space for a family of Hodge structures has those negativity properties that I mentioned, the biholomorphic sectional curvature and the holomorphic sectional curvature. Those translate directly into positivity of this Ricci form, and that's the bigness of the canonical. Here there's a nice open problem. This is, in the open case, this defines on the closure a 1-1 curve. So it's a differential form that has, if you like, mild singularities. It's integrable. And the conjecture is that you have an equation of currents where the Ricci form on the open part is given by this minus z, that's the divisor of infinity, plus the ramification. So this is some sort of almost generalization of a Gauss-Bonnet type theorem for the, in this case, for the canonical bundle to the parameter space for a family of Hodge structures. That I said earlier. And the second part of this talk, then I want to get more specific and show some calculations. Many of the calculations center around the Poincare metric on the disk. And tomorrow when I do the second part of these talks, taking this as the sort of toy example. So if you think of Picard's theorem, you have P1 minus 3 points, and you can say, okay, that parameterizes a family of smooth elliptic curves in a locally 1-1 way. Take the Hodge metric, that's the standard metric in the first cohomology of an elliptic curve. Look at its curvature. What does it look like near 0, 1, or infinity? And the answer is that it's going to be this will be its singular part at the origin in this case. Looks like the Poincare metric plus lower order terms. And that, is classical. You can find things like this in Alfor's book on complex analysis. The basic point is going to be that this toy example completely generalizes, and using it leads to proofs of the monodromy theorem, of the extension when you have a family of Hodge structures with no monodromy or finite monodromy over a punctured disk and so on. So tomorrow when I finish, I'll then turn to some specific sort of formulas that kind of give the feeling for what these curvatures of the Hodge bundles and the corresponding induced curvature on the tangent bundle to a parameter space look like and how they're used.
Is t a Hodge theoretic coordinate, like the exponential of the ratio of periods? Is that what t is? Your coordinate t. What is the t?
Here?
Yeah.
Oh, so you're on the punctured disk.
Yeah.
And t's just the coordinate.
But you could multiply with any invertible homomorphic function. Do you have a
Yeah.
specific t? Or
So I'm thinking of a normal crossing divisor, t equals 0 would be the equation of the divisor. So,
but it changes the shape if you multiply with the invertible homomorphic function, right? If you change your coordinate, you get a different
if you
thing.
change the coordinates, I mean, you just, so basically all you can do is scale. Suppose you take t and multiply by a unit.
Okay, that doesn't change.
Then you're going to get lower order terms in this. So really, this is the singular part of these differential forms that will turn up. Change of coordinates, you'll get lower order stuff coming in.
You say you somehow cannot do a change where you do it more severe as multiply with an invertible function.
Yeah.
You don't do that.
Thank you.